that point of time in array. Okay, so this is the problem statement, and we are going to start the discussion from this problem statement. So we have a new question in front of us, and this question says that you have been given an array. So for example, we have an array like this, 4, 1, 6. Okay, let's say we have an array like this of integer values. So you can see all the integer values are present. You have to find the minimum cost to remove all the elements from the array. What do you want? You want to one by one remove all the elements from the array, right? Now, whenever you remove any particular element, you incur a cost. Whenever you remove any single element, you incur a cost, and you have to minimize the total cost, right? So what is the cost you incur when you remove any single element, right? So whenever you remove any single element, the cost to remove any one element is equal to sum of elements at that point of time in the array. For example, let's say I want to remove 4 from this array. Okay, let's say in step number 1, we want to remove 4. If we want to remove 4, the cost that we have to bear is equal to the total elements in the array, sum of the total elements in the array. So what is the sum of the total elements in the array? 4 plus 1 plus 6, that is 11. So if you want to remove 4, the cost that you have incurred is 11. Okay, and now 4 is gone. What are the remaining elements? 1 and 6. Now let's say in the next step, you want to remove 1. In the next step, you want to remove 1. If you want to remove 1, what will be the total cost? Total cost will be the sum of the remaining elements in the array at that point of time. So what is the sum of the remaining elements? 4 is already gone. Remaining elements are 1 and 6. So 1 plus 6 is 7. So the cost is 7. This is also gone. And at last, you have to remove, let's say 6. So the cost is also going to be 6. Okay, the cost is also going to be 6. Now, what is the total cost of this whole operation? The total cost is equals to 11 plus 7, 18, plus 6, 24. Okay, this total cost is something that we have to minimize, right? There can be a strategy using which this total cost can be further reduced, right? This total cost can be further reduced. How do you reduce that? What will be the strategy that you will incur? And what is the final minimum cost after you apply that strategy is something that you have to figure out. What are the constraints? N represents the length of the array, and you can say that n can be as big as 10 raised to the power 6. Okay, this is the constraint that we have been given. Make sense, everyone? Very good, network. You're thinking in the right direction. Very good, Shubham. Yes. Very good, Jayant. Very good, Mahima. Very good, Shadan. See, a lot of guys already have the answers. What about the rest of the people? Bunch of people already have the answers. What about the rest of the folks? Very good. Very good. Great answers. Very good. I can see a lot of you guys are actually giving right answers. Yes. So let's start our discussion. A lot of you guys have the correct answer. Very good. So how can we actually solve it? If you carefully understand, then at any point of time, all the remaining elements add up to the cost. Okay, add up to the cost. For example, if you have 416, now just think about it. When we were about to remove 4, we summed up everything, 4 plus 1 plus 6. Then when we were about to remove 1, then we summed up everything again, 1 plus 6. And then at last again, we removed 6, so we were having 6 remaining. Can you see in this whole total, 4 plus 1 plus 6 for first removal, 1 plus 6 for second removal, and 6 for last removal? Can you see the contribution of 6 is coming 3 times? And don't you think the contribution of 6 is the biggest? How about, because of the fact that 6 is the biggest number in the array, we can see that 6 is the biggest available number. How about we removed 6 first? Then what will be the total cost? 4 plus 1 plus 6. Okay. But now in any subsequent removals, 6 is not going to take the part, right? If 6 will not take the part, definitely what will happen? Some other element is going to be added more number of times, which is less than 6. Hence, the sum is bound to be reduced. Now, for example, now between 4 and 1, if I will remove 1, the sum will be 4 plus 1. And then you remove 4 to give it 4. Can you see 4 is coming twice? But between 4 and 1, again, if I remove 4 first, then what will happen? The sum will be 1 plus 4. You removed 4. And now you are left with 1. Don't you think 4 plus 1 plus 4 and 4 plus 1 plus 1? Which one is less? This is less, right? Because the contribution of 4 you have reduced. So in every iteration, what we are trying to do is we are trying to reduce the contribution of the largest given element. At last, you have 1. So what is the sum now? This is 11 plus 5 plus 1. This is 17. So the minimum cost for this array can be 17. And can you see 17 is far less than 24? So what you can actually do is, the main trick is to reduce the number of times big elements actually participate in the sum or in the cost. How do you do that? How do you do that? Let's say we sort the array in decreasing order. Right? We sort the array in decreasing order. So what will you get? You will get something like 641. You'll get something like 641. Okay. Now take the total sum of the array. Take the total sum of the array. Take total sum of array. Right. And then in every iteration, remove the biggest element from total sum. From total sum. How do you do that? So first of all, if I write the code, you can say total sum is equals to 0. For I equals to 0, I less than n, I plus plus, total sum plus equals to array of I. Okay. So this loop, what this loop is going to do, this loop is going to take, first of all, calculate the total sum, right? And then we'll calculate total cost. We'll say total cost is equals to 0 initially. And we say, and we sort the array. We will sort the array, of course. So we'll say ARR dot sort. Okay. Right. We'll sort it in decreasing order. And then we will say, let's go to every element once again. Now, when you are at the 0th element, what is the total cost? The total cost incurred will be equal to the total sum of the array, right? Initially, when you are going to remove, let's say 6, the total cost is total sum of the array, 6 plus 4 plus 1. That we already have in the total sum variable. Now, for the next iteration, what you can do is, you can say total sum minus equal to array at I. Because for the next iteration, 6 is not going to be the part of the total sum. So can I say the total sum will be original sum minus 6, that is 5, right? That is 5. And at last, we can return total cost, right? So think about it. Initially, our total cost for an array like 641 is what? The total sum is 11. Initially, total cost is equals to 0. When you are at 6, in the total cost, you will add 11. And for next iteration, you will subtract 6 from 11. So this will become 5. Now, in the next iteration, when you're going to remove 4, you will add 5 to the sum. And you will subtract 4 from it. So you'll get 1. And then when you're going to remove 1, you will add 1 to the sum and make it 0. And can you see 11 plus 5 plus 1 is again 17. So this total cost is going to have your final answer. Swapnil, then you will again, like multiple times, you have to search for the largest element, right? To find the largest element, you need order of n time. And if you have to search for largest element multiple times, then the complexity will increase, right? It will go till n square. Swapnil, don't you think? Yes, but then why do you want to waste some space? Amit. No, Swapnil. So Swapnil, you are telling a wrong answer. Let me tell you why. So what Swapnil is saying is that, let's say you have an array like this. 1, 2, 3, 4, 5, Swapnil. Okay. You do not know this is sorted. You do not know this is sorted, but let's say you got it. Swapnil is saying, why not again and again search for the largest element? In the first iteration, the largest element is 5. You will go to 1. Is this the largest? No. Is this the largest? Is this the largest? Is this the largest? Is this the largest? Yes, 5 is the largest. How many iterations you did for finding the largest element? N iterations. Then in the second iteration, again, what you will do is you will try to find the largest element again, because you do not know now what is the next largest element. Yes or no, Swapnil? Then in the third iteration, again, you have to find the largest element. This n-based searching is going to come up again and again. Are you able to get my point? So that's why your answer is wrong. Now, guys, what is the time complexity of this approach? The time complexity of this approach, let's try to figure it out. Okay. What's the complexity analysis here? You can see this for loop takes order of n time, O of n time. Why? Because it goes to all the elements and sum it up. Then there is a sorting algorithm. Whatever is the complexity of the sorting algorithm, we will take. So for example, if you take something like merge sort, this is going to take n log n. And then again, this for loop is going for big O of n time complexity, because it is just going to every single element and do a few operations. So what's the final complexity? Final complexity is O of n plus O of n log n plus O of n, that is O of n log n, right? Because O of n and O of n are lower degree terms. O of n log n is the highest degree term. The final complexity becomes O of n log n. And what's the space complexity? Space complexity here is going to be the space complexity of the sorting algorithm, right? Whatever sorting algorithm you are picking, whatever is the space complexity of that sorting algorithm will be our space complexity, right? So in our case, if you are using merge sort, then the space complexity will go for O of n, right? Why do you want to write that? There is an already inbuilt method. I'm just saying, let's say if the inbuilt method uses merge sort. Okay. Now, guys, there's an interesting fact. Just a second. Okay. This internal sorting algorithm doesn't directly uses either merge sort or quick sort or any particular sorting algorithm, but actually it uses a combination of a lot of things. For example, there is something called as a Tim sort. Okay. There's something called as tim sort. You can see what tim sort does is that you can see Java, JavaScript, all of these languages, internal sort uses tim sort. Okay. So if you go to tim sort, right? You can see here, one second. Tim sort uses which algorithm? See, tim sort internally uses a combination of merge sort and insertion sort. Can you guys see that? Right. If you go for C++, which sorting algo C++ uses? Right. So C++ uses something called as intro sort. Intro sort is a combination of one second. I guess this uses heap sort also. One second. Now let's see intro sort uses which algorithms. Okay. So different languages opt for different things. For example, you can see C++ intro sort uses quick sort, insertion sort, heap sort. Right. So these are some combination based algorithms that based on the size of the array, based on the available memory, they try to take a call that whether you want to do a merge sort, whether you want to do an insertion sort, so on and so forth. Make sense? Why do we need all sorting algorithms? Every language has an optimized inbuilt sort, because every language has an optimized inbuilt sort which is dependent on these fundamental algorithms only. Can you see? JavaScript's internal sort is dependent on merge sort and insertion sort. Can I see that? Yes or no? Okay, cool. So I believe everybody will be able to implement it. The only fill in the blank that you have to do is how will you sort that in decreasing order? You need to pass a callback in order to make sure that you sort that in decreasing order. This is something that I'm leaving for you as a homework. Got it?